Hey, welcome back to Math with Patrick. Today's September 18th, and we are solving problem 261 from the Daily Epsilon calendar. And the answer today should be 18 because the answers for the calendar always match today's date. So this X right here should be the number 18. And it looks like to get this number 18, we need to solve this kind of complicated looking integral. And once we get some value for y, we can plug it in here, do this kind of fraction math, and we're going to get the number 18. Just so we can kind of concentrate mostly on this, how about let's just rewrite this bottom equation. We could multiply both sides by y and then divide both sides by x, just so we can isolate y. And so assuming that x is 18, we should get y is equal to pi over 18 for today. So if we get pi over 18 for our integral, then we have solved the problem. So I'll just kind of keep a mental note that this right here means y should be pi over 18. All right, now let's try to figure out the value of this integral. Again, should be pi over 18. We have technically an improper integral because we have an infinity at our upper bound. But our integral, it goes from 0 to infinity, and then we have this kind of fraction here, t to the power of 4 plus t squared over 3t to the fourth minus 3t squared plus 3, all squared on the bottom, dt. Okay. So just some initial integral strategies. Like I'm kind of thinking, could I do some u substitution on that? I'm trying to find like a chunk of stuff whose derivative also shows up, but I don't really see that because I would need some kind of power of 3 in my numerator instead of a power of 4. I'm also noticing I could actually factor out this 3. Like the in-between step is I would need to factor it out on the inside here. Not a 3 there. But I'd have t to the fourth minus t squared plus 1, and then all squared. So I could factor out that 3. And then when I have a product being squared, I can square each term individually. And then now I do have a 9 in my denominator. And since that is essentially a 1/9 in my integrand, I can take that constant coefficient out. And then I will simplify my integral just a little bit by taking out a coefficient in there. So we will get 1/9 of this new integral. T to the fourth plus t squared is still on top. And at least this way I have fewer numbers to worry about on the inside of my integrand. So actually knowing that this should be pi over 18, and overall we're doing something times 1/9, I actually know that this chunk right here needs to be pi over 2, because then multiplying by the 1/9 would get us to our right answer. So I'm actually concerned about proving that I want to show that pi over 2 is equal to this integral right here. Still from 0 to infinity, still the same numerator, but here I'm going to kind of remove that 3 and ignore the 1/9 for the rest of the problem. All right. Well, we still have a pretty difficult integral on our hands. I think the right thing to do here is to try to reduce some of our powers of t. So let's just try to target our integrand right now. Let's maybe divide the top and bottom by t to the power of 4. So something that looks like this. So this should still be equal because I'm dividing my numerator and denominator by the same value. On the top, I can distribute this denominator, and so I do get 1 plus 1 over t squared. And then in the denominator, I think it would make the most sense to me to actually kind of shove it in to the square here, although I would need to reduce this power to it too, because then if I distributed this exponent to both of them, I would still get t to the fourth in the bottom. And so I can divide each individual term by t squared, reducing that power to this. This is just a -1. This is a 1 over t squared, and this is all still being squared on the bottom. And with this, honestly, I had to look it up. A lot of the time, really like pesky u substitutions are really hard to find. I believe doing u equals t minus 1 over t is going to be the best thing to do here. I also need to figure out some kind of relationship between du and dt. So I could take the derivative of t, or with respect to t, of both sides. So I would get du dt is equal to 1, and then kind of using the chain rule and power rule here, I believe it's going to be plus 1 over t squared. And then I could say that du is the same thing as 1 plus 1 over t squared times dt. And then currently, though, so I see this part show up right here in my integrand, but I don't yet honestly see this part showing up down here. So I think I do need to square this u. So u squared is going to be t squared, and then plus 1 over t squared at the end, and then twice this product right here, which is going to just be a minus 2. And so it almost nearly matches what's going on in here. Just the value that I have is 1 less because I'm subtracting 2 instead of subtracting 1. So if I add a 1, then I am going to get exactly the value that I have in my denominator. So let's bring this u substitution into our actual integral. So we're going to have bounds. I don't know what they are just yet because I want to convert my t bounds into u bounds. But at least for now, I know that I can replace this numerator with the dt as just a du off to the side. I'll put a 1 on top to just kind of fill the space. And then in the bottom, I do have u squared plus 1 all squared. So our bounds were 0 to infinity in terms of t. And so that means I could plug in those values here and then get different bounds to then use for my u integral here. So plugging in an infinity on the top, this grows to infinity. And then this number right here is essentially 0 because 1 divided by a really big number is going to be basically 0. So my upper bound stays the same. It's still infinity. And then when I plug in a 0, this number right here is 0. And then when I plug in a 0 here, 1 over 0, kind of with this limit idea, is an infinity, though we are subtracting that value of infinity. And so I do want a negative infinity for my lower bound in terms of u. And I still am not done with substitution. To me, I think the easiest thing to do now is to do a trig substitution here. I think what I want to do is call u equal to tangent of theta, I believe, with the idea that, well, u squared is tangent squared of theta. And then also we could do du d theta is equal to secant squared of theta. And I'll just multiply that theta over to the other side. I know I'm not supposed to like multiply and split differentials this way, but at least for the purposes of this problem, I can. And then I also need to figure out what my trig substitution here is. I have a tangent squared plus 1 right here, and I just want to double check what that's supposed to be. I'm really confident in my knowledge about this trig identity, equals 1. And I always forget how to like produce the one with tangent squared myself. And so I do know that like starting from here, tangent is the same thing as sine over cosine. So if I divide everything by cosine squared, then I should get a tangent somewhere in this new identity. So we do get tangent squared theta here. We get plus a 1 because it's the same thing on the top and bottom. And then 1 over cosine squared, I could just use the reciprocal function there, which would be secant. So I could do secant squared theta like that. Cool. All right. So let's replace our du with a d theta, and then I'm forced to put a secant squared theta on top. And then in the bottom, I can replace u squared plus 1. That's the same thing as tangent squared plus 1. So I could replace that with secant squared theta, And then I can't forget that there is already a square on that one. And then, okay, I think I need new bounds though, because these are bounds in terms of u, whereas these need to be bounds in terms of theta. And so I would need to think, okay, what value of tangent would produce an infinity, and what value of tangent would produce a negative infinity? And I think the best numbers to pick here are going to be pi over 2 and negative pi over 2. Okay. And then we could simplify the integrand again. We do have secant squared on top, and then secant to the fourth on bottom. So overall, that's 1 over secant squared theta, which is actually just the same thing as cosine. I'm essentially just re-flipping it around here. Using another reciprocal identity, I do have cosine squared theta, d theta, integral from negative pi over 2 to pi over 2. And this cosine squared has a power reducing identity. Cosine squared theta is equal to 1 plus, cosine 2 theta all over 2, I think. Hopefully I'm right. And then I could replace my integrand with that. I am going to split that divide by 2, just so it's a little bit easier for me to approach both parts. I'm going to keep the same bounds, d theta, and then I guess we could solve. So let's see. This part right here, I could actually just kind of do geometrically, because here I'm also imagining that I'm splitting my integral into 2, something like this. So I'm imagining like if I have a graph and I have the value of 1/2 right here, then if I take the integral from negative pi over 2 to pi over 2, this distance right here is going to be exactly pi. And then this distance right here is going to be that same 1/2. And it's just a rectangle. And so the area of that rectangle is going to be the product of its dimensions, which is pi times 1/2. And so this gives us pi over 2. And that's actually kind of what we wanted out of this, right? We wanted this whole thing to be pi over 2. So I'm really hoping that this other part produces a 0 right here. So we're going to add on, let's see, what happens here? Well, actually, isn't this an even function? Right? Because cosine normally starts at the peak here and it kind of goes down like this. And then it has those troughs at pi and negative pi. And then so if I apply this graph transformation, this times 2 in the middle, that would give me a horizontal compression where I don't need to plug in a pi anymore to produce my trough, but I only really need to plug in a pi over 2 because it's like over 2 and times 2 will cancel out. So this graph would have those troughs at negative pi over 2 and pi over 2. And then normally the peaks and the troughs of cosine functions are at 1 and negative 1. But this divide by 2 is just going to reduce the value by a factor of 2. And so with these graph transformations in place, this times 2 and divide by 2, I still maintain the even function. And so when we're taking the integral of this, we can also think about this geometrically. And we can see that the bounds are from negative pi over 2 to pi over 2. And actually, hold on. Yeah, okay, no, so we're still fine. Because this positive area right here is completely canceled out by the negative area right there, because the cosine function is like symmetrical like this. And then the same thing happens over here. The positive area that we find in this chunk perfectly cancels out with that chunk. So let me actually mark it with essentially saying negative area, positive area, positive area, negative area. And the integral here, just thinking about it geometrically, is 0. So there we go. Basically, we got pi over 2. And that's exactly the value we wanted out of this integral. And so if that integral is pi over 2, then this one right here is pi over 18. And then that's exactly what we wanted, right? We wanted pi over 18 to be equal to y, so that once we plug it in here, we do get 18 for x. So there is my solution for today's problem. Quite the long one, I would say, but I hope you enjoyed, and we're all done. I'll see you tomorrow. Bye.